I dedicate this video to one of my subscribers at Anti-Regular. I hope you find this useful. An introduction to talk for uni-level physics, first year uni-level I'm assuming. Let me know how you find this video, if the content is useful. That would be great, thanks. So this idea of talk pops up just about everywhere, not just in physics, but also in engineering. I don't know if you've seen those ads on TV. I think it was Kia, Australia, and they were showing off their utes, one of their utes, and it said something like 440 Newton meters of torque. And torque in that case is basically just, in the context of cars, automotives, is the engine's ability to do work, to do something like tow heavy loads or accelerate really quickly. But anyway, it also pops up in things like biomechanics and health sciences. The best way I can define torque is the measure of the tendency of a force to cause rotation about an axis. I think that's the best way to put it. The key word here is rotation. So torque, you can think of it as like a rotating force, loosely speaking. It's not quite correct, but that's how you can really picture it. It's causing basically something that causes rotation. I'll illustrate with a very simple example, and I'll throw literally a spanner in the works. Here's a spanner. So before that, actually, I'll draw a nut, yeah? So a nut is like a hexagon structure. Okay, it's a piece of metal. You see things like this in construction, in cars, say, to basically fasten with bolts to hold parts together. I'm sure you've seen this before. They look like this. So side on, here's a nut, and here's the bolt. It's got like a thread sometimes, like this. But it's essentially like a screw, if you wish, loosely speaking. It's like a screw, it holds things together. I'll draw it side on. So here's a nut, okay. And a spanner is basically a tool that turns these nuts and bolts. So it looks like this. Excuse my drawing, it's not really good, but I'll do the best I can. I'm sure you've seen a spanner, it looks like this. Okay, and its outer portion here matches, so if you get the right span, it matches the outside of the nut. Okay, so this is called a spanner. Okay, these pop up all the time in torque problems. Now in the US and Canada, in the North America, it's called a wrench sometimes, okay? But in Australia and the UK, it's called a spanner. Now the center of the nut, this thing here is called the pivot. The pivot is the point about which the spanner causes it to rotate. So it's a center of motion here, in other words. Okay, it's also known as a hinge, but pivot is what it's commonly known as. The length of the spanner that goes from the pivot all the way to the end of the spanner, that's called the lever. Lever is basically a distance. It's what's known as a vector. It's got size and direction, right? And this will be useful for when I define torque mathematically. Sometimes this length is called lowercase r for short. And let's suppose I apply a force with my hand at 90 degrees to the lever vector. Okay, a vector is something that has size and direction. Okay, sometimes we write it as r with the arrow on top. Okay, anything that has an arrow on top is a vector. Without the arrow, it's just got size. So I'd say scalars are more, so a scalar, the scalar of the lever is just r, the length of the lever. Let's say, I don't know, 30 centimeters. The vector version of this lever, r with an arrow on top, is 30 centimeters, let's say, I don't know, west, as an example. So vectors are things that have size and direction. For example, wind's coming in from the north at 20 k's per hour. That's a vector. I weigh, I don't know, 80 kilos. That's a scalar. It's just got a size. It doesn't tell you direction. Force in physics is a vector. It's something that has size and direction. So I'll put an arrow on top there. Suppose I'm applying a force at 90 degrees. Here's a 90-degree angle here between the force vector and the lever vector. So we'll start with this scenario here, and I'll now define torque. So torque, so I should say the applied force, in order to cause rotation, it can't be parallel to the lever vector r with an arrow on top. This is very important. And if you think about it logically, it really makes sense. I mean, if I apply a force coming in this way, right, parallel to r, it's not going to cause rotation. It's got to be perpendicular, right, to cause rotation. Perpendicular means at 90 degrees. Let me tidy up this diagram a bit. So I'll quickly derive an expression for torque. Okay, suppose I apply a force at some angle theta to the horizontal. Let's say the horizontal is established by the line where the lever vector is acting along. So that's theta here. Let me zoom in a bit. It's getting a bit messy. Okay, this line here, that's the horizontal. Apply a force this way. Let's call it force F. Angle theta here. So the angle theta is below the horizontal. So I'm applying a force going down to the right. Now to find the perpendicular component, the angle that's at 90 degrees. So this force here, any force that's at some angle to the horizontal theta, you can break it up into components, into the y and x components. In other words, it's got a y component going downwards like this, and it's got an x component going to the right, okay? Because it's going down and to the right, it's got to have a component going down and a component going to the right. The horizontal component here for the force is F with an x at the bottom, F sub x. And the vertical component is an F with a y at the bottom, F sub y. So we need to find F sub y, that's what we're interested in, because that tells us the perpendicular component to the horizontal. That's what we're interested in, because that's how we get maximum torque. So using basic trig, let me blow up this triangle here again. Looks like this. Theta, that's F sub y, and that's F. Now, to get an expression for F sub y and F, we need to use sine. Sine theta is opposite over hypotenuse, because F sub y here is the opposite, and the F is the hypotenuse. So F sub y is the opposite, F sub y. The hypotenuse is F, so ignoring directions for now, put out the arrows, because we're only interested in size, magnitude. So from this, using algebra, we find that F sub y, the vertical component, in other words, is just F sine theta. And torque is just, so torque is given the symbol tau, lowercase tau. It's a Greek letter from the Greek alphabet. And that's equal to this force here, F sine theta, times r. Okay, r is the distance between the pivot and the very end of the spanner in this case, the thing that's causing rotation. So that's your formula for torque. Now the units for F is newtons. So F is the applied force. It's given the symbol capital N for newtons. The more newtons, the more force. Theta is angle, that's measured in degrees. And it's the angle I should specify here. It's the angle between the lever vector, so R in other words, and the applied force F. Okay, that's measured in degrees. And R is, I'm running out of room, I'll do it here. R is the distance between the pivot and the point of applied force. And in physics, distance is given the typical unit of m for meter. So in other words, R is the distance. So where I've put R here goes from here, the pivot, all the way to the point of application. In other words, where you basically touch the spanner and apply the force, that's where R is. And then tau, torque, has units of Newton meters. Okay, newtons from the force F and meters from R. And that's it really, that's the formula for torque. And that's a simple definition of torque. There's a bit more complicated version involving something called the cross product. I'll get to that later. But for now, that's torque. Now, maximum torque, just a note, max torque. So the most amount of torque you can squeeze out of anything, like a spanner, is given by this. It occurs when theta is 90 degrees. In other words, you have to apply a force 90 degrees to the spanner in order to get maximum rotational force about the pivot here to turn the nut. You can try this at home if you have a spanner in your garage and a bolt lying around. It works. So in other words, tau sub max is given by R sub perpendicular F. In other words, when the lever vector is perpendicular to the force vector, that's when you get max torque. So if you look here visually, if you think in terms of pictures, that's what I've done here, right? So the angle here is 90 degrees between R and F, the applied force in the Y direction. Check out my other video that I made on torque for HC physics. There's some really good visual representations of what's happening. So I encourage you to look at that video here, video on my channel. But here is just a bit more theory than the other video that I made. I'll give you an application in, let's say, health science. This is very useful in health science, particularly in chiropractic. So in a chiropractic practice, when you apply a force to a joint at a certain distance from its pivot, you're generating torque. Okay, and that's really crucial in things like adjustments and spinal manipulations. I know a couple of mates who are actually chiropractors, and they tell me that they use this all the time. Also, when you're opening a door, right, you see this effect all the time. If you push a door near the handle, far from the hinge, the farther away you are from the hinge you push, the easier it is to open. Right, if your hand is close to the hinge of the door, it's going to be a bit harder, right? So it's got to be a bit further away. Let's do an example. See how this thing works. Let's suppose you're testing a patient's deltoid strength, and you apply a downward force on the delt of 50 newtons. No, sorry, I should say, let's suppose you're applying a downward force of 50 newtons to the patient's forearm. So the forearm is here, here's the hand. You apply a downward force like this, 50 newtons, that's a lot of newtons. And let's say the forearm is, let's say the pivot, so the shoulder joint is here. Let me zoom in a bit. Shoulder joint is there. And let's say the forearm is this distance here, 0.3, so 30 centimeters away from the shoulder joint, the pivot. Let's work out the torque, how much torque is needed. So torque, as we know from before, is given by maximum torque. So torque is given by RF sine theta. So the first step is to write down the formula. R is 0.3, F is 50 newtons. Now maximum torque occurs when theta is 90 degrees. Now if you punch this into your calculator, so sine 90 is just 1. 0.3 times 50 is 15 Newton meters. So 15 Newton meters of torque is applied to the shoulder joint. okay, for the deltoid strength, to test for the deltoid strength. And just a note, torque, because torque is a vector, okay, it's got an arrow on top. Torque can go clockwise or counterclockwise. Okay, and usually direction is specified. Let's say clockwise means negative direction, counterclockwise means positive direction. I'll give you an example. I'll give you a question to do later. We can do it now if you want. Suppose a 60 Newton force is applied at 45 degrees to patient's forearm, 20 centimeters, so 0.2 meters from the elbow joint. Torque is question mark. So you got to find the torque there. So that's torque in simple terms. Now torque comes also in another form. Okay, now for my subscriber at anti-regular, I'm not really sure with the course you're talking about, but I have a feeling that this next form of torque is relevant, I think. Let me know in the comments. So there's a bit more of a complicated variation of the torque concept involving something called cross product. And that's if you study vectors, first year uni. I did that many years ago, so I'm not an expert in it. I did it many years ago, but it's a lot of the stuff that you do at uni. If you don't use it in your everyday day-to-day job, you sort of not forget it, but just really need to take some time just to get familiar with it. So I had to do a bit of thinking with this, and eventually I got there. So another way to express torque is as follows. So the same torque, T, et al., R crossed with F. Now this cross here is not a multiplication symbol. It's known as the cross product. Okay. It looks simple. It's not really simple per se, but it's just a compact version for expressing torque in the following way. So this is useful for, let's say, scenarios involving vectors with three components. So suppose you're dealing in three-dimensional space, so in the case of chiropractic, when you move a joint, you're moving it, let's say, in three directions. Three directions of motion: up, down, back, forth, left, and right. Okay, that's what 3D means. 3D looks like this. So you've got the X and Y axes, but you also have the Z axis. Now, we put a hat on top. Okay, it looks like this. It's a symbol. I call it a hat because it looks a bit like a hat. You're familiar with the X and Y axes that go vertically and horizontally. There's also another axis that comes in or out of the page. That's called the Z axis. The Z axis, Z, Z, same thing. And suppose R, in this case, is given by three components: X1, Y1, Z1. And F also has three components. Let's call them X2, Y2, Z2. Okay, so this is for torque calculations in three-dimensional space, in 3D. Now, I don't know if you do this stuff for chiropractic in first year, but this is the idea. Now you need to sort of commit this to memory. So to calculate this cross product, here's what you do. I'll rewrite this. Torque is R crossed with F. Now, because each of these two vectors has three components, here's how we write it. Now, you write these massive vertical lines. It looks a bit like an absolute value, but it really isn't. You've got I. Now, yeah, okay, I'll put I, J, and K. I'll put hats, X, Y, and Z hat here. They should really just be I. So I is the X, put X in brackets, X direction. J is the Y direction, put that in brackets, the Y. And Z is the K direction. So that's K with a hat on top. So the hat just indicates direction. That's all that indicates in this case. So I'm going to make this a bit cleaner, tidy this up a bit, the X's and Y's. So I'll put the X's in the first column here. X1, X2. These are the two components of the R and F vectors. Similarly for Y, the J hat vector, y sub 1, y sub 2. For k, that's z, so z1, z2. Now these fancy lines here, from memory, it's called the determinant, if I'm not mistaken. Determinant allows you to determine the cross product. That's where the word comes from, determinant. So let's calculate it. Now the rule of thumb is this. This is sometimes called a matrix, the way this is arranged here. But I don't think you really need to know it for this case. But anyway, to calculate the determinant, here's what you do. And I'll highlight as I go along just to make it easy for you. Use different colors, I color code it. So you do y1, z2, you multiply these together, just straight multiplication, minus z1, y2, like so. Put brackets around them. And then it's minus, it's getting a bit messy here. Use purple, minus x1, z2, x1's here, z2's here, minus z1, x2. So z1, x2, comma, the third component of the calculation is, let me use light blue, x1, y2, minus y1, x2. Now this is something you need to commit to memory. Sometimes I put these funny brackets around to indicate that these are the components along the x and y direction. So the calculation will give you this. And I'll show you how this goes in practice, okay? So this formula you have to commit to memory. I suggest just practicing with anything when you're learning something new, just practice and eventually it commits to memory. So we'll do an example. So suppose, e.g., suppose we have a position, I should say, suppose we have R lever vector from the pivot to, so the pivot, let's say is a shoulder to the point of force. Let's say R is just, doesn't matter what R is, 0.2, 0.10 meters. And let's suppose F, force applied to the arm, is given by this. Okay, so 3 components for each vector. We need to work out the component of torque. So this is the way you should be thinking about this in each direction. Okay, there's 3 directions here, X, Y, and Z. Now the formula for torque is R crossed with F, and that's equal to, remember, I, J, K, so that's X, Y, Z, X1, X2, Y1, Y2, Z1, Z2. Okay, with these big vertical lines, the determinant. So we need to work out this determinant thing. So if you recall, it's just y1, z2 minus z1, y2. So there's this 2 by 2 arrangement here. Brackets, comma. Minus x1, x1, z2 minus z1, x2. Close bracket, comma. Last component, x1, y2 minus y1, x2. Okay, that's your formula, and that's about it. And the rest is just, so that's the hard bit. The easy bit is just substituting. So I'll put equal sign here. I should have done this before, but that's okay. So for this bit here, the I, J, and K. So the x1 for the R, so this here is for the R vector, and that's for the F vector. R vector is 0.2, so that's the X component, X1, Y1, and Z1. So X1 is 0.2, Y1 is 0.1, and Z1 is 0. F vector is 0, 50, 0, so 0, 50, 0. Okay, let's do this. Let's work out the components. Okay, torque. So this here is the X component of torque. That's the Y component of torque. And that's the Z component of torque. Okay, so the torque is as follows. Let's do it. Y1 is 0.1 times Z2, which is 0. That makes life easy. Minus x1 z2, so x1 is 0.2. Make sure we put brackets too. Z2 is 0. Again, it makes life easy. Makes life much easier. And x1, so the next component, x1, y2. x1 is 0.2, y2 is 50, minus y2, x2. y2 is 50, x2 is 0. Close bracket, and that's it. So if you punch these into the calculator, we'll just use your head, you can get this. So that times 0 is 0, that times 0 is 0, 0.2 times 50 is 10, and that cancels out. So that is your torque. That's the torque in 3 directions. So in other words, what this is telling us is that the torque points along the z-axis. Okay, only one direction in this case. Hopefully they give you these styles of questions in an exam or an assessment. It's just easier to work with. It's less fiddly. And I'll let you do this next example here. This next question. Suppose R is this, 0.3, 0.2, 0 meters, and F is 0, 40, 30 newtons. I hope this video helps. Try and work through it bit by bit. So start with this very simple definition here. Think of a nut and a spanner. A bit of trigonometry here, how I'll work through that. The general basic formula, RF sine theta. And note that the max torque occurs when the force is perpendicular to the lever vector. And then the cross product is working through this here. And hopefully that helps. Let me know in the comments.